Hi class. So today we're going to use what we've learned last class about expected value to analyze a lot of different mixed strategies for a game. We're going to try to figure out, is there a best mixed strategy? Is there an optimal strategy for us to play if we know the payoff matrix of a game? So I'd like to just start with an example of a game. This is called Matching Pennies. Okay, it's a two-player game, and player one gets to show either heads or tails on their penny, and player two likewise shows heads or tails on their penny. And player one is trying to match player two, and when they match player two, they win. They're both heads, then they win 5 points. They're both tails, they only win 1 point. And if player two is able to successfully guess opposite of what player one does, then they'll win 3 points in either case. Now, when you take a look at the game like this, it seems pretty balanced. Why does it seem balanced? Well, player one can win kind of 6 points overall between his two options. Player two can win 6 points themselves between their two options. And so maybe it's a fair game, right? I mean, they both have the opportunity to win 6 points. Well, let's take a look and see if that's actually the case. So what I'd like to do is analyze a bunch of different mixed strategies for player one. So to give a mixed strategy, I need to tell you with what probability player one will choose heads, and with what probability player one will choose tails. And so let's start with a relatively simple mixed strategy. We'll say he chooses half and half. So literally player one can just flip their coin, cover it, and then unveil it to player two, right? There'll be a 50% chance that they throw a heads, there'll be a 50% chance that it's a tail. What I'd like to do is I'd like to analyze how well it does against player two's strategies. So let's calculate the expected value versus player two choosing heads, and the expected value versus player two choosing tails. Right, those are the two options for player two, and I want to know how well is our strategy going to do against those. And so let's remember, how do we calculate expected value? We're going to take the outcomes that we have, we're going to scale them by the probabilities that they occur. And so right now, our strategy is given by half the time will be in row one, and half the time will be in row two. That is, half the time we choose heads, and the other half the time we choose tails. Okay, but which outcome are we going to have? Well, just because I'm in row one, I don't know whether it's going to be 5 or whether it's going to be -3. Likewise, even if I'm in row two, I don't know whether it's going to be -3 or 1. And so what happens is, well, it depends on what player two is doing. And so this is why I'm going to break it up into the two cases. The first case, when player two is playing heads, well, then what are our two outcomes? They're going to be 5 and -3. And the second case, when player two chooses tails. And there, our outcomes are going to be -3 and 1. All right, so let's go ahead. So, in the first case, we're looking at player two choosing heads. Our outcomes are 5 and -3. We have our probability over here of each one occurring. The top one will occur half the time, the bottom one will occur a half the time. So our expected value is going to be 5 times 1/2, which is 5 halves, -3 times 1/2. I'm going to add these together, and I get 2 halves, which is 1. So if I play half and half, heads and tails, and player two chooses heads, I'm going to expect to win 1 each time. Now, what about if player two chooses to use tails instead? Then we're no longer in that first column, we're in the second column, and so the outcomes change, and therefore the expected value will change. It'll no longer be 5 halves and -3 halves. It'll be -3 times 1/2, -3 halves, and 1 times 1/2, 1/2. Notice the probabilities stay the same because my strategy, this is the same mixed strategy, just that the outcomes changed. So what's the sum of these two? Looks like it's going to be -2/2, which is -1. So my strategy versus player 2 choosing tails all the time is going to actually make me lose more. And if we think about both these situations, it just makes sense, right? If player 2 chooses tails, then I'm switching between -3 and 1. So, and I'm going to have both of those occur the same amount, so I should expect to lose more than I gain. Likewise, in the first case, when player 2 chooses H, I'm bouncing between 5 and -3 an equal amount of the time. And so I should expect that maybe I'm going to eventually start winning more than I lose. So let's compare this to pure strategies that we have. So one way to show a pure strategy is just to say that I'll choose H with probability 0 and I'll choose T with probability 1. Right? This just means I'm always choosing T. Okay? If you want, you can still emulate it with this chart over here, 0 and 1. Now what's going to happen if player 2 chooses H? Well, remember, I'm always choosing T, so my expected payout is just going to be that -3. And what's going to happen if they're always choosing T instead? Well, then it's going to be T and T, and so my expected payout will be +1. I could have done the multiplication across, but I mean, 0 times anything is 0, and 1 times anything is exactly that 1. You can check. This is exactly what will happen. Okay, let's do the opposite pure strategy of always choosing H. So I'm choosing H with probability 1, T with probability 0. Maybe I'll show you that the math really does work out in this example. So let's do the first case when player 2 chooses heads. Then I'm going to multiply across. 5 times 1 is 5. -3 times 0 is 0. And so my expected value is 5. +5. Okay, well again, that was kind of obvious because I know I'm always in this first row, and so the intersection is going to be 5. Nothing really brilliant right there. And what's going to happen if player 2 chooses T? Well, again, my outcomes are going to be -3 and 1, but it's going to be -3 times 1, which is -3, and 1 times 0, because that'll never happen, so my expected outcome will be -3. And so if we just look at the examples that we've seen so far, this mixed strategy is kind of balancing out these kind of big payoffs, right? So this is a big loss, this is a big gain, and this mixed strategy is kind of giving us a nice value in between. We're sort of hedging our bets. Same thing, this is an okay win, this is a big loss, and we're hedging our values, we're hedging our bets by doing a mixed strategy of doing half and half. Okay, so let's look at 2 more mixed strategies. I want to look at what happens if I choose heads most of the time, and tails not so often. 2/3, 1/3 is going to be my split now. And what happens if I choose heads 1/3 of the time, and tails 2/3 of the time. One thing I want to point out is that since there's 2 options, the probability I choose tails is always 1 minus the probability I choose heads. If you think about why, well, they both have to add up to 1, so 1 minus this probability has to be this probability. Okay, so let's take a look at this 2/3, 1/3 one first. Let's look at this row. Again, each row is a different mixed strategy. So let me put my probabilities up here. I have 2/3 and 1/3. And I want to find the expected value versus H. So my outcomes are going to be 5 and -3. So I'll multiply them across. 5 times 2/3 is 10/3. -3 times 1/3 is -3/3. And so altogether, I have a value of 7/3, which is equal to 2.33. So on the whole, I'll be winning about 2.33 points every time. And what's going to happen if I do it against tails? Again, my probabilities don't change. It's just the column I'm looking at that changes. Well, now I have negative 6/3 and 1/3 here. So altogether I have 5/3 negative. And what's that equal to? That's negative 2.67. Negative 2.67. So you see, this is slightly hedging my bets between this wild swing of 5 and -3, depending on what player 2 chooses. There's a slightly narrower gap between these two expected values. And over here, there's an even narrower gap, right? And so as I decrease the probability that I choose heads, it looks like I'm having a smaller gap between how well my strategy performs against heads versus performing against tails. And note that I don't get to choose which of these columns I'm in. This is all up to player 2. So if player 2 knows that I'm using this mixed strategy, what do you think they're going to start throwing? Well, they'll throw tails, because if they throw tails, they know I'm going to get that as my expected value. Okay, so it seems tough to shake the idea that, our strategy really depends on what player 2 is doing. In fact, this is a 2-player game. It seems like, why would there ever be a situation where it doesn't matter what the other player is doing? But let's calculate this last mixed strategy right here of 1/3 and 2/3. So what if I choose heads 1/3 of the time and tails 2/3 of the time? Put those probabilities up here, 1/3, 2/3. Let's calculate the expected value versus heads. So I have 5 times 1/3, 5/3. Negative 3 times 2/3, negative 6/3. So what's the total answer? It's negative 1/3, negative 0.33. How does my payout change if I'm going to switch to from versus tails instead? Well, I have negative 3 times 1/3, that's negative 3/3. And 1 times 2/3, that's going to be negative 1/3 again. So what's going on? My expected value versus them playing heads is actually exactly the same as my expected value against them playing tails. And so hold on. This is saying that it doesn't matter whether they play heads or tails, I'm going to get the same payoff. So what's the conclusion here? I can guarantee myself an expected value of negative 0.33 no matter what player 2 chooses, heads or tails, if I decide to use this split of 1/3 and 2/3. Okay, this mixed strategy is sort of safe against whatever player 2 chooses. It doesn't depend on what player 2 chooses. I'm going to have the same expected value. Okay, what would be nicer if it was guaranteeing me a positive expected value, but nevertheless, I can guarantee myself expected value of negative 0.3, regardless of player 2's choices. If we choose the mixed strategy of heads 1/3 of the time and tails 2/3 of the time. This makes our expected value versus player 2 choosing heads equal to our expected value versus player 2 choosing tails. If we compare it to all the other mixed strategies suffered from the fact that if player 2 caught on to what we were doing, they got to choose what they were doing. They could always choose the lower of the two numbers. They could make us lose a lot of money. But with this one, since they're equal, they can't choose to make us take the lower value. So we're guaranteed to get this value no matter what. Well, that sounds like a definition we talked about. Turns out the value of this game is just negative 0.33. Again, because it's the score I can guarantee myself every time. And it might feel weird because, again, expected values aren't actually a score I can get, right? I can't actually get negative 0.33 points. But in the long run, I can guarantee that this is going to be my score on average each round. Any other strategy I choose, I can't guarantee myself something that good, right? Negative 3 is worse, negative 1 is worse, negative 2.67 is worse, negative 3 is worse. And so what we saw is that choosing a particular mix strategy is going to be able to guarantee us an outcome regardless of what player 2 does. And this is exactly how we find a value of a game. It's the score that I can guarantee myself. All right, now I want to think about whether or not we feel like this game actually is fair. Well, let's see. If I were playing this game, even with my best strategy of minimizing my losses, no matter what player 2 does, I can still only guarantee myself losing 0.33 every time. That definitely doesn't sound fair to me. Now, what would be fair? Well, what happens if I could guarantee myself plus 0.33 every time? Would that be fair? Well, no, because then player 2 would feel like they were losing out on that game. And so our definition for fair in these types of games is going to be that the value is 0. And so this game is not fair. Player 2 is going to win eventually in the long run. Now, if we go back and look at this table, it might feel like we sort of just lucked into the right mixed strategy, right? Like, oh, we just happened to figure out that 1/3, 2/3 gave us that these expected values were exactly the same. In general, we might not be so lucky that we're just trying out a bunch of mixed strategies that we get the expected values are the same, right? So what I'd like to introduce you to is the idea of finding formulas for this expected value and using those formulas to solve for that probability where we're going to get equality. So let's add an extra row to this chart. But instead of saying what number the probability will be, we'll leave it as a variable. We'll leave it as the variable p. So p is just going to represent the probability we pick heads. Well, if we pick heads with probability p, then what's the probability we're going to choose t? Well, remember the relationship between the two columns, they should add up to be 1. And so over here, the probability that we choose t is going to be 1 minus p. If you think about it, p plus 1 minus p is equal to 1. So that's the complement probability. Now then, what's the expected value against player 2 choosing heads? Well, how are we going to figure that out? It's the exact same as what we did before. Instead of putting numbers here for probabilities, though, I'm going to use variables. So my probability of choosing heads was p. My probability of choosing tails was 1 minus p. And so what's going to happen when I multiply the outcomes by those probabilities? Well, let's see. Up top, I have 5 times p. In the second row, I have negative 3 times 1 minus p. Now I want to add those two up. I'm going to get 5p plus negative 3 times 1 minus p. And now I can distribute and simplify. I'll get 5p plus negative 3 times 1 minus negative 3 times p. So that's 5p minus 3 plus 3p. And I can simplify that even further just by combining all the p's, 8p minus 3. So my expected value versus them choosing heads is going to be given by the equation 8p minus 3. Well, let's do the same thing against tails. My probabilities stay the same. There's still these variables, p and 1 minus p. But now, in the first one, I have negative 3 times p. The second one, I have 1 times 1 minus p. And so let's combine those by adding them together. Negative 3p plus 1 times 1 minus p. And I'll distribute. Luckily, 1 is pretty easy to distribute. It looks like I'm going to get negative 4p plus 1 by combining all my p's together. So I now have a formula that tells me what my expected value versus h is and my expected value versus t is. I'm going to call this EV sub h. I'm going to call this one EV sub t. And let's just test them out. What happens if I want to choose heads half the time? Well, then I'm saying p equals 1/2. And what is EVH when I plug in 1/2? Well, it's just 4 minus 3 is equal to 1. And what's EVT when I plug in p equals 1/2? Negative 4 times 1/2 plus 1. Negative 2 plus 1 is negative 1. Well, hold on. If you just take a look at what we've already done, that's just telling us the expected values that we got from before. So now we can test out any mixed strategy we want just by plugging in the probability we're going to choose heads into these EV equations. And if we're interested in that point where the two expected values are equal, well, then what should we do? We can solve for when EVH is equal to EVT. That is, I'm going to get the same payout when they play heads as when they play tails. That's going to give me this moment up here, where my expected values are the same. This is when it doesn't matter what the other player does, I'm going to get the same payout. So let's give it a shot. Let's solve these equations. 8p minus 3 equals negative 4p plus 1. You can add 4p to both sides. 12p minus 3 equals 1. I can add 3 to both sides. 12p equals 4. Finally, I can divide by 12. P is equal to 4 over 12, which is 1/3. And look at that. That's just saying that these two expected values will be the same when the probability that I choose heads is 1/3. And that's completely in sync with what we saw in our table before. When the probability of heads was 1/3, that is what was giving us this nice equality between the two. So we're going to give a name to this special mixed strategy. It's called the optimal strategy for playing the game. Once we find the optimal strategy of a game, we can find the value of the game by plugging this p-value back into our equations for the expected value. Let's see what we get. Well, EVH was 8p minus 3. So if I plug in 1/3, I have 8 times 1/3 minus 3. Well, that's 8/3 minus 3. We plug that into our calculators, we'll get negative 0.33. Look at that. That's exactly the value of the game that we solved from before. So as you can see, this idea of letting p be a variable for how often we should choose heads versus tails, and knowing how important calculating expected values is, can tell us a lot about these games that seem like a whole game of chance, right? How do I know what they're playing? If they play tails, then I should play tails. If they play heads, I should play heads. So what do you mean there's a strategy? What are you talking about? Well, it turns out there is a strategy, and it uses probabilities, and we can guarantee ourselves a certain value by making sure we play our optimal strategy. All right, thanks for listening. I know this material is getting a little bit crazy, so I'd highly recommend you take your time through this video, go back and rewatch the examples, try the worksheet, and rewatch the video at the same time, and that'll help you to understand the material a little bit better. Good luck. Let me know if you have any questions. Take care.